Hi, my name is Tom McCurdy. I'm with Aerzen USA, and this is my presentation. Um, this has been challenging to try to record this thing. I've tried a number of different technologies, so hopefully this time will be the charm and I can get my message across and you'll find it interesting. So here we go. So if you've ever had children or if you ever were a kid, chances are you've seen Winnie the Pooh. And one of those characters in Winnie the Pooh is a guy named Tigger. And Tigger is basically, he represents unbridled energy and zest for life. And this is where it kind of converges with the high-speed turbos or the integral gear turbos, which have a tremendous amount of energy, a tremendous amount of efficiency. And it's a machine that can sometimes be challenging in terms of understanding it and controlling it, and controlling the aeration, which is basically the whole objective of a large aeration blower. So the idea for today is to basically give you a little bit of a better understanding of the turbo blower and other efficient blower technologies. Try to simplify some of the complexities here. We'll get into sizing, proper sequencing, and effective control of aeration, which is basically the two keys of proper control. So what makes a turbo so great? And I call a turbo, whether it be airfoil turbo or magnetic bearing turbo, or even single stage integral gear turbo. What makes them so great? Well, first of all, they're highly efficient. And that efficiency has been proven since at least 2004, where it can be as much as 30% more efficient than a positive displacement blower or a multi-stage centrifugal blower. It is depending on the technology, it can be more affordable, especially if you're considering the life cycle costs. It's a completely integrated package. High-speed turbo is completely integrated with an onboard VFD, onboard control system, the motor, the impeller, everything is all self-contained. And then finally, it's limited in terms of the maintenance that you would need to do on a blower. Basically, it would just be filters only. So let's look at that high efficiency. If you compare some of the other technologies like positive displacement blowers and what we call our hybrid, which is a low pressure screw compressor, you could see in terms of the performance that it really does well versus a standard positive displacement technology. Here's one example and another example, and then a third example. So you get the idea. It's pretty well established that it is efficient. And it is more affordable. And I said before that the life cycle cost is probably one of the biggest factors involved here. In this example here, though, you'll see that the turbo is actually the lowest capital cost of the three that we were looking at here. And the energy costs were pretty much neck and neck between the low pressure screw and the turbo. And the other factor is turn down, which is the ability of a blower to reduce its flow to its machine minimum. And you could see there were some advantages there as well. It is completely integrated machine. So this short video is going to show you what I mean. When the enclosure starts to come off here, you could see all of the individual components that I'm talking about. You've got the turbo itself, which I'll show you in a second, which is direct connected to the motor, a high-speed inverter or VFD, and then a blow-off system inside the package, as well as a control panel right here. So let's look inside the heart of the machine, which is the turbo blower, impeller, and motor assembly itself. This is what gives the turbo a big energy advantage, and this is pretty much a revolutionary type concept. And it starts with that motor, the high-speed synchronous motor, and the type of bearing that's being used. And you could see that this red is the airfoil bearing. And within that bearing, between the surface of the bearing itself and the surface of the rotor, there is a microscopic layer of compressed air, which is at about 40 bar, which is about 600 psi, which is pretty remarkable. And this is where it derives its strength. So this thing can operate at such a high speed without lubricants and basically without any frictional effects. And in the event of a power failure, it will just basically coast to a complete stop. Now, if you look at a magnetic bearing, that is basically a similar principle in that it is a high-speed motor, but instead of airfoil bearings, you have a series of magnets, electromagnets, that keep that rotor in place while it's rotating at such high speeds. So the issue with a magnetic bearing is that you have a whole series of those electromagnets, and you basically have to constantly feed it power so that those magnets are energized. And you could see where all those electromagnets are currently located. And with that comes its own power source. So instead of it being a passive type bearing, it is an active bearing that needs its own power supply and needs basically its own battery backup. So, both machines, both technologies are very robust, but again, they both have their challenges. So to give you a little history, high-speed turbo, especially the airfoil bearing, sprang out of a division of Samsung out of South Korea. And from that came three companies, Neuros, K-Turbo, and Antle. And when they came over to the North American wastewater market, APG Neuros was a subsidiary company that basically marketed and eventually manufactured their own machines in the States. K-Turbo, that technology was purchased by Aerzen. And for the Antle process, that was licensed by a company called HSI. So there were quite a few turbo blowers that came out. I mean, they took the market by storm. And with that were some good and some bad installations. With any new technology that comes into the market, there's always going to be a certain level of a learning curve that goes on with that. And some people actually got, for lack of a better term, burned by some of the initial offerings of the high-speed turbo with the airfoil bearing. And there was a certain retreat to the magnetic bearing turbo. And the biggest company, or the first company that was out there involved in that technology, was a company called ABS, and they've been since purchased by Sulzer, so you're probably familiar with that. But was that the holy grail of the turbo market? Well, ABS actually kind of beat the airfoil turbo bearing, or airfoil bearing turbo technology to the market. They had their first installation in the US in 2004, which was well ahead of the airfoil bearing turbos, but they really weren't part of that whole wave of turbomania. And that may have been a business decision or a marketing decision, whatever the case may be. They had the first ones, but they didn't really have a big majority of the market. What followed afterwards was Atlas Copco, which bought HSI, and most recently Kaiser, which bought a company called Pillarator, and both of which have magnetic bearing turbos and are currently in the market. Well, maybe some people were burned by the magnetic bearing turbo, and they basically put them all in the same bucket and said, I'm not using this technology, I'm going to something else. And therein came to somewhat of the emergence of the rotary screw, or the low pressure screw compressors. Aerzen has what we call our hybrid. I mentioned that before. Atlas Copco, who had purchased, like I said, purchased HSI, had their ZS. Kaiser had their offering. So again, it was all to meet that market demand for high efficiency machines. But was it the panacea? Again, was it the holy grail? Well, the low pressure screw definitely had some advantages in that it was basically a complete package, indoor, outdoor enclosure. It's quiet with the enclosure. It does have high efficiency when especially as the pressures go up. It has a high turn down. Because it is a mechanical piece of equipment, there was no such thing as surge, and you could control the unit with a standard VFD. Some of the limitations came when you had really low pressures. And as it got bigger, you had more metal, so it's a higher footprint by comparison to a centrifugal machine. All right, so maybe just throw all those into a bucket and say, hey, you know what? I do like these centrifugal machines. Let's go to a brand new, or should I say a brand new old technology, which would be the integral gear turbo, which was basically, it was basically started, or one of the first ones was a company called Turblex, which you may have heard of. They generally were residing in some of the bigger horsepower markets, and I'll get to that in a second. But since then, they have also joined, they've also had competition from Lone Star, Howden bought Turblex. I call it HSI 2.0 because it was basically the same company that was once HSI. And then Continental and Next Turbo. So those may be familiar names to you. Again, is this the way to go? Who knows? The benefits, definitely high efficiency, great turn down. But you could use a standard NEMA motor here. You weren't looking at a high-speed specialized motor like I showed you in that previous video clip. And you don't need a VFD, which is very interesting because all of these high-speed units with the high-speed motors and the high-speed impellers all needed a harmonic filter. And so that added to the expense of a high-speed turbo. With this, you don't need it. You don't need a VFD because of the way it's controlled. And if you don't need that VFD, then you don't have those electronic harmonic distortions that would go basically back into your electrical supply. So another advantage. And you can use medium voltage. And this is why I had said before when we talked about Turblex, that when you get above a certain horsepower, like say 500 and above, typically that starts to get into the domain of a 4160 volt motor or medium voltage, whereas the high-speed turbo was basically all 480 volt. So there's a certain potential advantage there. And these can also go the higher horsepower, 1,000, 2,000 horsepower, which up until very recently was never really the domain of the high-speed motor in the high-speed turbo. But it is louder, it's typically more cost, it's a larger footprint. Limited pressure variation is basically the domain of any other, any centrifugal unit, but it is mechanically intensive. If you look at the insides of it, you've got inlet guide vanes, you've got discharge diffuser vanes. It's very mechanically intensive. You've got a lot of linkages in there. You compare that with the high-speed turbo, where instead of mechanical linkages, you have a high concentration of electronics. So you basically, you for lack of a better term, try to pick your poison. So why were blowers such a big target here for efficiency? It's all in how much energy they use in the plant. By far, the biggest consumers of power in a wastewater plant are the aeration blowers, probably 50 to 60% of the energy bill. And I have been told by a number of utilities that it can be as much as 4% of the municipality's overall power usage. So to save power, in this area is kind of a big deal. So with the high-speed turbo or with the integral gear turbo, they are both pretty smart machines. And by smart machines, I don't mean iRobot smart machines, but I do mean that they need to understand, that they need to live by some certain laws. So to borrow the Isaac Asimov rules of robotics, you could see a robot may not injure a human being through inaction or allow a human being to come to harm. If we look at the laws of turbo blowers, a turbo may not operate in an unsafe manner that causes harm to operators or to itself. Pretty neat analogy. The second law of robotics, or the second law of turbo blowers, is the robot must obey the orders given by the human beings, except where such orders would conflict with the first laws. Well, what do you know? On a turbo blower, it must provide all the air required for the system, as long as such orders do not conflict with that first law. So it kind of fits in pretty well. And then the third law, well, nah, there's no third law. So, but you get the point. The idea here is that the blowers must satisfy the system requirements and protect the blower simultaneously. So it has to run right in that center of that Venn diagram. So what the limitations are basically the design of the impeller itself, where the operating parameters must fall within the confines of this individual curve, from the standpoint of flow, which is on the x-axis, and pressure, which is on the y-axis. And it cannot go into what they call surge, where surge is basically where the machine is providing more air than what the system needs, and the system starts to give back. So you start to get backflow. And there are plenty of examples out there that will show what the effect of that backflow is, like this. You could see this is a turbo blower on a ship. And so, this was pretty non-destructive occurrence, but for high-speed turbo blowers, it could be destructive if left uncontrolled. And there's the Tigger analogy. And so every blower manufacturer has controls to keep that blower out of surge. Likewise, overheat is where you're basically putting so much flow through that unit that you're not able to build up temperature. And if left, again, unchecked, it can go sonic. If I move this out of the way here, you could see it's a picture of an airplane going into supersonic, where you've got a shock wave. Well, that would be just as destructive as surge if left unchecked. And like I say here, you're going at 40,000 RPM. And it's not only the impeller that's going that fast, it is also the motor that's going that fast. Hence the need for control. Why else does a turbo blower need to be smart? Because of the profusion of electronics that are within the cabinet. And again, this applies regardless of the type of bearing that's being used. You've got a very specialized inverter assembly. You've got this high-speed motor and impeller assembly. You've got blow-off valves. All of that is controlled by the central processing unit within the blower itself, or the blower package itself, integrated and smart. So what does it mean to the system? What if you have multiple blowers? The two major items in terms of control are sequencing the turbo blowers if you have more than one in the system, and proper aeration control. So the idea is that you need a master panel, or one panel to rule them all. So this gets into the controls aspect of it. And I'm going to come back here, and I'm going to stop recording for a second. So now you've got identical turbo blowers. How do you sequence them? You've got 3 blowers there. Each one of them has their own characteristic curve. The challenge here is when you're sequencing these blowers, what is it, how can you add and subtract blowers into the system and still operate safely? That first law there. So let's take a look at that. If you have one blower that's servicing the system, and then you want to add a second blower into the system, the basic rules in sequencing that come in the programming of the master panel will look like this. You'll have one blower that's basically, during the low flow periods, serving the system. When it gets to the point where the flow requirements are getting beyond what the single blower can safely accommodate, that blower will automatically go back into the center of its range, basically the widest spot in this performance map, so that any disturbances by the addition of more air would be basically buffered, and you'd still be running in a safe zone for that blower. So second blower comes on, they both run in parallel, satisfying the needs of the system. When the end of the day comes around, or evening, say when you're, everybody's going to bed, and you're running on the low side for both blowers, again, signal goes from the master panel that says unload that second blower, and that first blower is going to take on the loading in the system. Likewise, when you're adding a third and fourth blower, you're basically repeating that. So it's a relatively simple process, but you really have to tell your turbo blower what to do in order to sequence it. So that's with identical size blowers. There are some systems that would use a jockey blower. And a jockey blower is basically a smaller blower that would handle the lower end of the control range if the primary blowers were basically size so that the lowest flow is not optimal. So, but one thing you have to do when you are using that jockey blower, especially when you're in the design phase, is to make sure that you're handling the summer maximum, which is when the air is at its lowest density, as well as the winter minimum, to make sure that, again, with the change in density from summer to winter, this directly impacts a centrifugal blower's performance. But the most important thing is to make sure that you have sufficient overlap between the minimum of the bigger blower and the maximum of the smaller blower, regardless of the season. So this is a critical area of control when you're going from small to large or from large to small. What if you don't have a jockey blower? What I have seen, some of these engineers have specifically designed in power wastage, meaning if the aeration basins are still seeing high dissolved oxygen levels, like say in the middle of the night on a cold winter night, and if you have be right back. The hazards of home recording. Anyway, some engineers actually design in inefficiency, which boggles my mind, which you're basically, and this is an actual engineer drawing, which shows the blowers going into a discharge header. And in that discharge header is an actual bypass. I'm going to blow that up for you right here, so that if the blowers are turned down to their absolute minimum and the dissolved oxygen level in those basins is still running high, they get rid of the air that they spent, this power, this energy to produce, only to throw it away. all for the sake of controlling the dissolved oxygen in the basin. Now, I understand the biological aspect of it. I don't understand why they would design a specific way of wasting the energy in that blower. So here is one way that proper control can actually help during those periods. And if you look at this is a graph of an actual plant, where is it? North Carolina. And you could see that Sunday night into Monday morning, the dissolved oxygen levels, or the demand, was very, very low. And so what took place during those periods was the way that the master control panel was controlled. For that zone, the turbo blowers were unloaded and reloaded. This blower has the capability of basically running an idle, where the blow-off valve opens up and the RPM of the blower slows down to a bare minimum. So it's like you're running in neutral. The comparable control mode for a magnetic bearing blower would be to basically be in a no rotation mode, where the magnets are still energized, but they're holding that rotor basically in a non-moving position. So you're really minimizing the amount of energy that you're using. And you're also halting the supply. Now, the key with the control is you could see these jagged lines here. And these jagged lines are basically the on and off sequencing, or the not on and off so much as the load and unload sequencing. The intervals of the time are such that it's off for a period to let the dissolved oxygen drop down, but not so long that you lose the mixing, that you don't want your sludge to start settling. So it's a balance that is achieved here through the proper controls, and no diving into the basin. So let's move on to traditional aeration control. This is not, we're going beyond sequencing. We're going to the point where we're feeding the right amount of air into the aeration system. And traditionally, it was a pressure-based control. And a lot of systems that are still out there still have this pressure-based control. And here's what it looks like. You could see that that the pressure-based control is based on this pressure set point, okay? This is what the static curve looks like, or the operating curve looks like. So there's a big gap between the pressure set point and the design pressure of these blowers. Here's the reason why. You've got your supply of air going into each section of the basin, starting, you've got your anoxic zone, then you've got two other steps of aeration taking place. And each one has its own dissolved oxygen sensor, and each of those sensors controls the positioning of the valve. And so you've got each one basically like a separate system. And so and then once the net pressure in the header reaches a certain point based on the positioning of those valves, the blower will speed up or slow down depending on where that pressure is in reference to its set point. So it is basically what they call cascading loops. You've got 3 cascading loops here, and then you've got another cascading loop here that's controlling the blowers themselves. So a lot of times they can be conflicting with each other. They could be fighting each other. But the points that I want to make are that there's a lot of wasted power here. You're basically using anywhere from 10 to 15% more power, depending on where you are within this curve, than you are. And this basically is wasted power that's you're kind of building into the system. And because you're running at a higher pressure, you're also running the risk of subjecting those turbo blowers to a surge event. So there are a lot of things going against this traditional control. The improved control, which is something that had been developed and approved by EPA, is what they call most open valve. You can go most open valve with a pressure type control, but most of the time you get the maximum efficiency out of a flow-based most open valve control, where you've got basically these three dissolved oxygen probes, one per basin, like we were talking about before. But instead of individually controlling the valve for that particular zone, it takes those DOs, basically determines what the flow is that is needed for each of these zones. And the zone with the most need for air has the valve that is the most open. So the most flow is going through that, and typically you're measuring the flow, and that flow is either increased or decreased by the valve right there. But that most open valve basically will drop that system pressure so that you're running in the most energy efficient range for the blowers. It helps avoid the surge conditions, and it optimizes the system pressure. So this is a big leap over and above the pressure-based control. So the next thing, and we're almost done on this, is that controlling the rate of change of the air supply into the system. You know, having most open valve is all well and good, but how quickly or how slowly you were opening and closing those valves, or increasing or decreasing the flow on your blower system, is basically the icing on the cake that really will help you control your dissolved oxygen more easily and more effectively. The traditional method is PID control, proportional integral derivative. And it is really best suited for linear responses. And aeration basins are anything but linear. You've got the response rate for low load versus high load. You've got the response for the diurnal flows over the course of a day, combined with those BOD loadings. And so even like if you have an industrial plant that's also contributing into the system, that can spike things as well. Then you've got seasonal variations, as I showed you before with the turbo blower performance curves. Those seasonal variations will impact the amount of air that's being supplied to the system based on the density of the air. Likewise, the biology is going to be affected by the seasonal changes, which are going to affect the temperature of the water. And then there's the control of the valves themselves, which is anything but linear. You see here on this diagram, this is a curve that shows the amount of flow going through a given valve based on its position. Again, anything but linear. You know, typically when you are about anywhere from 80% closed to fully closed, it starts to get what they say asymptotic, and the amount of closure of that valve becomes very, very, it needs a precision in terms of the actuator. And you can see the linear curve here is, the actual valve itself is not even close. So what is the heart of PID? Well, what it'll do is it will respond to the changes that are put upon it in terms of the set points. It could either go hunting, which basically says, like say that the dissolved oxygen is high. Well, we got to close that valve. And so the amount of closure on that valve will result in a drop in the dissolved oxygen at that analyzer. And so it'll make an adjustment based on, oh, we've overshot it. We got to go back. We got to, and again, up and down and up and down. If it's well tuned, you minimize that oscillation. If it's over damped, then you're on the opposite side where you're not responding quickly enough. So all of these are impacting the amount of air that gets delivered to the system over the course of a day. And meanwhile, you've got changes that are taking place simultaneously in the water that's coming in. So what will happen is not only will you have issues with the dissolved oxygen, but you will also be basically overworking your valves and your actuators. And you could see based on this curve here where the airflow target is and where the actual airflow ends up going. It's a lot of action on the valve and a lot of basically premature wear and tear on all of those components. So what do we do? There is available what they call a self-tuning algorithm, which is more of an adaptive control. And you can see by the list here, the programming actually learns the process. It learns the history. Again, we're getting smart again. We've got, maybe not a robot there, but you do learn the process. It adapts to the daily and the seasonal changes. The blowers and the valves will work together so you don't have that hunting, and you can basically help eliminate the surge events. And what this is proven to show is that versus manual control, you can save up to 41% on the power bill. You've got these very efficient blowers. It's all in how it's feeding the process that's really going to derive the most benefit out of the efficiency that these blowers have to offer. Compared to PID control, you're probably saving 20%. Still, 20% is very good. And then that's on top of the most open valve, so you're operating at a lower pressure. So the benefits and the savings start to multiply after a while. And again, kind of reviewing the rate of change. If you look at the PID versus the self-tuning algorithm, clearly there's a lot less valve action. So again, this just points out some of the savings that you could have and some of the, decrease in the wear and tear in your system. Here's an example from a wastewater plant in Maryland. And I was saying industrial customers, where in this case, a dairy farm pumped 800 gallons of cream into the wastewater. I mean, clearly it was a mistake on their part, but you could see the spike in kilowatts because of the extra air that was being used, but the system handled that spike. And based on what their baseline was, their audit baseline, and their and where they actually used the power, they were able to qualify for a $150,000 rebate, and it basically funded most, if not all, of the process upgrades. So, here's a real-world example of how it benefited a customer. So, what are your takeaways on this? When you're looking at blower upgrades, and with the over 16,000 wastewater treatment plants in the U.S. alone, there are basically blower systems that are nearing the end of their useful life, or they're maybe consuming more power than they could be otherwise. So the selection of that blower technology, whether it's PD, which would include those low pressure screw compressors, or centrifugals, determine based on what the characteristics of your system are. That'll basically determine what type of blower technology you end up using. High-speed turbo technology, whether it's airfoil, magnetic bearing, or even in-grille gear turbo, is a smarter technology than either PD or screw, which is a very basic technology. So you've got that smartness. The turbo must be controlled. And hopefully you're getting that, you know, based on the high speed that we're talking about and the precision that's required in that process, that system needs to be controlled. And if you're of a certain age, you probably remember this movie with Will Smith. And finally, the objectives of the controls would be to safely sequence the blowers for all conditions and to satisfy the air demands as efficiently as possible under all conditions, regardless of season, regardless of flow, regardless of BOD loading. So hopefully you've learned something here. I appreciate your time. And apparently I'm going to be taking questions while you're watching me and I'm watching me. So hopefully you're fired away. Hopefully you're able to you know, get all of your questions answered. So thank you for your time.